So we are studying the curve fitting and interpolation, and in the previous lecture we looked at the polynomial regression, and we specifically looked at the quadratic regression, and then we studied how we can use and utilize Lagrange polynomials to, you can say, for the curve fitting and interpolation purposes. And we also studied some drawbacks of the curve fitting and interpolation method using the Lagrange polynomials. So the basic, you can say, the drawback was that our previous calculation was not or cannot be utilized for the newer calculation if we have the increase in the data set. So, and we said that the Newton's method is basically, you can say, the remedy for that drawback that the Lagrange polynomials had. So unlike the Lagrange interpolation polynomials, the Newton interpolation polynomials are recursively constructed. So these are basically recursive and dependent on the previous one. So these are the Newton divided difference, you can say, polynomials. So you can see that the first degree polynomial is this, and the second degree polynomial is using the first degree polynomial with addition to one term, and similarly the third degree polynomial is using the p2x with addition to one term. So basically these are this is, you can say, recursivity which is mentioned here, right? So in general, well, the nth, you can say, the order Newton divided difference polynomial can be represented by, if this is n, then this one is Pn minus 1, and this one is basically n plus 1. So if it is nth order, then you can say there is one addition in the coefficient. So for example, if it is first order, then we have two, you can say, the coefficients a1 and a2. Similarly, if we have p2 or the second order, then we have 3. So it is almost, you can say, one addition to the coefficient level in terms of, you can say, the degree of the polynomial, if you see that. So since P1 must agree the data set, so this is generally the same. For example, if P1 is the first degree polynomial that pass between the 2 points, if it pass between these 2 points, then it must satisfy these 2 points. Alright, so if it is passing through these 2 points, then these two conditions must be fulfilled. For example, if we put x1, let's say that this is point 1 and this is point 2, and if we put x1 here in place of x, then we must get the value y1, right? Because we are saying that it is passing through that point. And similarly, if we put x2, then it must be equal to y2 because it is passing through that point. So we can equate these equations and use these equations to find the values of a1 and a2. How we are doing that is that, because we know that this will be true, so we put x1 in that first order, you can say, polynomial, and when we put that, we get this equation, and we know that this must be equal to y1. And similarly, this equation, when we put x2 here, this must be equal to y2. So after solving this equation, we get these two results, that a1 will be equal to y1, alright, and similarly a2 will be equal to this quantity, which is y2 minus y1 over x2 minus x1. Alright, so this was, you can say, the first degree Newton divided difference polynomial. Similarly, we see that p2x, the second degree polynomial of the Lagrange of the Newton divided difference polynomial, because the first degree passes through the 2 points only, which we just discussed. Alright, so x1 y1 and x2 y2, but the second degree polynomial is passed through the 3 points, and these will be x1 y1, x2 y2, and x3 y3. Okay, so you can see here that for the second degree polynomial we have this equation, right? So it also must satisfy if it is passing through all these points. So if we put x1 in the, you can say, the term of in this equation of the second degree polynomial, if we put x1 here, it must be equal to y1, alright, because it is passing through that point. And similarly, if we put x2 it should also agree with y2 because it is passing through that point also, and similarly y3 must also agree with x3. So we can see that the only addition the p2x has is this term here. Alright, so you can see here is that this term is basically the addition. Alright, so this term is only the addition here in the value of p1x. And if we put x is equal to x1 here, so for example, if we put x is equal to x1, so this term will become 0. Alright, similarly, if we put x is equal to x2, this term will also become equal to 0. So this term will only operate when we put x equals to x3 here. Alright, so in that term it will not cancel out. So because it will you can say cancel out when we put x1 and x2 here, so for the values of x1 and x2 we can use our previous coefficients a1 and a2, which we calculated in the you can say the first degree polynomial. Alright, so because the third point is only adding to the last term, it is not having effect on any other or the previous terms. So if we put x3 here in replacement of x, so we can get this equation, this p1 x3 is equal to a3 x3. So we are putting just the x3 in place of x. So we know that p1 x3 is basically equal to this equation. This is the first order. You can say this is the first order equation. Alright, so if we put x3 here, so this is basically that equation. We have just put the value of the first, because p1 indicates the first degree polynomial, Newton divided difference polynomial. So we have put in the value of this equation. So if we solve this you can say equation, we solve this equation and put the values of a1, which is equal to y1, we have just calculated in the first slide. So and this was equal to y2 minus y1 over x2 minus x1. So if we put a1 a2 and solve this you can say equation for a3, we can get this equation. So this is basically the formula for a3, just like we did for the a1 and a2. So we can continue this process. So if we move on towards you can say the third degree polynomial, the only addition would be the a4 value. Alright, so we can use these a naught, a1 and a1, a2 and a3 values. We will have to calculate the value of a4 just. All other values could be used based on the previous calculations. So we can observe some common trend or the pattern here. Alright, so you see that basically our a1 was equal to y1 and our a2 basically is equal to y2 minus y1 or x2 minus x. We can say that this is the function of x2 and x1. Alright, so we can say that at x2 its value is basically y2. Similarly at x1 its value is y1. Right, so it is basically differentiating between these values and these values. So y2 minus y1 and x2 minus x1. Similarly a3 value, which we just calculated, we see that it's function of both x3, x2 and x1. So it is basically first we have x3 and x2, this minus x2 and x1, this second. So there is a common pattern here. So basically if we calculate this one, this is basically y3 minus y2 based on this pattern over x3 minus x2, and similarly this one is y2 minus y1 over x2 minus x1. Similarly this one is y3, so just similar because this is not the function, right? So we have seen the common trend here. So basically this a3 we calculated is just the same as these equations here. Alright, so we can find the general trend here. So if we have you can say ak plus 1, we can use the similar trend to calculate the value of that a function. Alright, and similarly we have seen that Our polynomial is basically, if we put the value, complete value of this here, and then complete value of this here, we can calculate, or we can come up with the nth expression of polynomial of the Newton divided difference, which will include a1 plus a2x plus a3x. So basically these are the addition with the increase in the number of n. So this is, you can say, the general form or the nth degree divided difference interpolating polynomial. So these, you can say, the coefficients can be best calculated using the divided difference table. So this you can say we have observed that there is a pattern between the formulas for a1, a2, a3, a4, and so on. So we can calculate it using this table. So basically these are the data points: x1, x2, x1, y1, x2, y2, and x3, y3, and so on. So our first a1 is basically just the y1 as we calculated. So our next a2 is basically the function of these two, or the differences of these two. So this is basically y2 minus y1 and x2 minus x1 divided by x2 minus x1. Similarly, this we can calculate this function also, which is equal to y3 minus y2 divided by x3 minus x2. Alright, so our a3 function is based on these two functions. Alright, so it will be this quantity minus this quantity over x3 minus x1. Right, so we can keep on going forward and get the values of a3, a4, a5. So if we compute this table, it will be very much easy for us to calculate the value of these, you can say, the coefficients. So we can see an example here, and it will all be clear that how we can formulate the Newton divided difference table. So consider the data in the table and use the second degree interpolating polynomial that goes through the second, third, and fourth data points. So we have to use just the second, third, and fourth data point and use the second order Newton interpolating polynomial. And we have to calculate the value at x is equal to 0.35. So these are the data points. All right, so 0.1 and 0.120, 0.2 and 0.225, and 0.5, and y value is 0.4650. So these are the data points. So we can calculate this value by subtracting y values divided by x values. So we calculated this value based on that. Similarly, we can calculate this value based on, and this value this y value minus y3 minus y2 and x3 minus x2. All right, so this is basically this value. And now to calculate this value, we have to just minus these y values and the corresponding x values. So basically it will be 0.7973 minus 1.084 and 0.5 minus 0.1, because these are, you can say, going back towards these points. So this is basically the value of a3, a2, and a1. So we know that the polynomial for the second degree interpolating polynomial will be like this. So one way to remember this is that because we have 3 points, there will be 3 coefficients. All right, so there will be 3 Newton, you can say, Newton divided difference coefficients, and you can see the pattern here also, that if the first one is a1 and the second one is a2 x minus x1, and the third one is basically x minus x1 minus x2. So basically the index of the coefficient, these x values are basically 1 less than the indexes of the coefficients. So you can remember these interpolating, you can say, interpolating polynomials by seeing their pattern. So when we put these values of a1, a2, and a3 in here, we get this polynomial. This is basically, you can say, the line which is, this is basically the equation of that whatever, you can say, the line that is passing through these points, or the best passing through these points. So if we replace x to be 0.35 here, all right, so it is best passing through these points. So it is not that it is best passing, so it will exactly pass through these points. So when we put x is equal to 0.35 here, the x value should be replaced with 0.35, we will get the interpolation value, which is 0.3595. So this is how we can solve it. So now we will consider the same data, but now we will use the fourth degree Newton interpolating polynomial that goes through all the data points to find the interpolating value of n. So because there are 1, 2, 3, 4 and 5 values, so it is basically fourth degree polynomial, and there will be, you can say, the maximum up to a5, the 5 coefficient based on the number of the data points. So as we know that it is a fourth order, we have to calculate the fourth order polynomial. So we can write the polynomial p4 of x is equal to a1, and you can see that it is following the same pattern up to the a5, which will include the index up till, you can say, the one less than the index of the coefficient. So this is how we can do it, and these are the 5 points that were given to us to formulate. So the first one value is basically, because a1 value is equal to y1, so the first value is basically the same, which is y1. a1 is 0, and the second value here we can calculate by this same formula, which is y2 minus y1 divided by x, this 0.1 minus 0. So we can use this formula. Similarly, this value will be calculated in a similar pattern, 0.2258 minus this 0.1210 divided by 0.2 over 0.1. So this method will be just the same, the y values minus the x values. And similarly, this 0.4650 minus 0.2258 divided by 0.5. So this value. So similarly, this value 0.6249 and minus 0.460 divided by 0.8 over 0.5. So we get these values. And you can observe that our a values are basically at the top of these. Right? So basically, this is a1, this is a2. Right? It's calculated now. A3 will be calculated using these two values. Right? So it will be 1.0480 minus 1.210, and up the x values will be up till their roots. All right. So this one will be 0.2 minus 0. So you can see that this is the A3. Similarly, we can calculate the remaining two in the same column, and then when we calculate this one, A4 value, it will be minus 0.626 minus or minus you can say become plus 0.810, and the x values will be the corresponding root values, which will be 0.5 and 0. Right? So it is, you can trace out that it is 0.5 and 0. And when we move on towards the A5 value, it will include both the 0.8 and 0. Right? And it will, the y values will be these two values, 0.266 and this. So it is very easy to draw the Newton divided difference table using just the similar formula, that y of you can say the higher value just like y2 minus y1 over x2 minus x1. So it is basically the same formula that can be used to apply to the all table, and with the increment of every value we will be able to calculate these coefficients very easily. When we calculate these coefficients, we can just place these coefficients in our polynomial, and after placing that, you can say these coefficients here, we get this you can say equation which represents our polynomial that will pass through these points. So when we put the value of our required interpolation, that is x is equal to 0.35, because we want to find the value at 0.35. So when we put x is equal to 0.35 here, we get our answer to be 0.3577. So this is how we use the Newton divided difference table and Newton divided difference formulas to calculate and formulate the interpolation of the data.